Hi, this is Dane Quinn from the University of Akron. For today's video lecture, I want to talk about one of the, I think, coolest examples of how you can use kinematics to do other things, and that deals with power. And in particular, the power across a mechanism. So the idea is that we can actually use a velocity analysis to relate the forces and moments that act on an ideal mechanism. So we do that through the external power of the forces and torques that are applied to a linkage. So here, for example, let's consider a bar, right, that happens to be rotating, right, possibly with angular velocity, omega, and we'll describe the bar as b, which means that the end of this bar has a velocity, v of p, in sort of this direction. So now, if I think about a force that's applied, say at the end, then the power due to that force is force dot velocity, right? So essentially that's equal to the force itself, F, dot, then the velocity, V of P. So again, if I know the force and I know the velocity, I can calculate the power. Alternatively, if I had a torque that was applied to this bar, right, so maybe I've got a torque from a motor, T, that's applied here at the pin, then the power due to that torque is equal to the torque itself, T, dot, then the angular velocity of the object. So again, I can calculate the power based on the input forces and torques, but then together with the kinematics of the mechanism. So what we're going to do here works for ideal mechanisms. So what's an ideal mechanism? Well, if you look at the energy of a system, it's always conserved, right? Energy is conserved. So that means that the net power is equal to zero. Well, the net power of an object is composed of power due to dissipation, and then change in kinetic energy and potential energy, right? So this is essentially the stored energy, and then the external power that acts from, say, forces or moments. So if we have an ideal mechanism, what that means is that we are able to eliminate a couple of these, well, three of them really. So in particular, there's no internal losses, right, or no dissipation. So here, this term would go to zero. Again, because we assume for an ideal mechanism that there are no losses. Then we also assume that these mechanisms are rigid and massless. So if they're rigid, then there's no elastic deformation, which means that there's no change in potential energy. And if they are massless, then there's no kinetic energy. So there's zero stored energy within the system. These are actually not bad assumptions. Typically, our mechanisms are very stiff, so the deformation within them is very small. Think about an aluminum rod right here in a linkage. In addition, these mechanisms are typically very light relative to the forces that are applied to them. So if you looked at a kinematic chain that was transferring force within, say, construction equipment, then the forces that are applied to that mechanism are really, really much larger than the inertial terms of the mechanism itself. So it's not such a bad assumption to assume they're massless and rigid. Now, if we throw away the dissipation and our kinetic energy goes to zero, or our change in kinetic energy goes to zero, and there's no change in potential energy, then the only thing left is that the external power has to vanish. So for this ideal mechanism with, say, n external sources, so n is some number, right? Typically, in our case, it'll be 2. Then the total external power, and the total external power is the sum of the input power from all of the individual sources, has to be equal to 0. So if you look at the power from, say, this force, and then you look at the power from this torque in this example here, then they have to vanish. In particular, in this example, right, I've assumed some directions for the force and the moment. The power due to the force, let's call that P1. And so that's going to be F dot the velocity of the endpoint, P. The power from the torque will be P2, so that's going to be the torque itself, dot the angular velocity of the bar. And again, that implies that P1 plus P2 equals 0. So we have another relationship now between the force and the torque. Moreover, the velocity components, so the velocity of P, the angular velocity of the bar, they can be related through kinematics, right, which is exactly what we're studying here. So we can use our kinematic relationships and this power relationship then to relate the force and the torque acting on the object. And again, I think this is kind of cool because when we do this, this ends up being equivalent to satisfying static equilibrium conditions. So remember our equilibrium conditions from, say, statics, dynamics, and general mechanics. And it was sum of the forces equals 0, acting on the entire mechanism, and sum of the moments equals 0. Now, I'm not saying that the sum of that this force has to balance out this torque, because of course that's impossible. There are different kinds of objects. But if you remember, a free body diagram of this object would also include reaction forces here at the pin. And we'd have to figure out, if we were to apply static equilibrium conditions, what those reaction forces would be. I'd have a momentum balance, angular momentum balance, linear momentum balance. Essentially, I would solve for the reaction forces along with a relationship between T and F. But in doing so, like I said, I have to do a whole bunch of work to deal with those reaction forces. Here, if we use this external power, then the reaction forces never appear. So we essentially can relate the external effects directly without incorporating reaction components and reaction forces. And again, we're able to do that because we can determine kinematics of the mechanism and use this equation. I will point out that this only works for ideal mechanisms where the total external power vanishes. But as I said before, that's not such a bad approximation for a lot of the different situations that we'll be looking at. And it does provide sort of an upper limit, in a sense, to the torque that you could get out of applying a force to this bar, for example, or vice versa. So let's actually figure out how this works. Now, for this link, we find that the angular velocity is simply theta dot in the k direction. Right, so that's going to be our angular velocity in terms of this angle theta. And the velocity of p here, well, here comes our kinematics. It's the derivative of the position, right? So if L is the length of this bar, and it's in the I2 direction, then we have the derivative of Li2, which again we'll use our vector derivatives, we'll use our kinematics. That's L times the angular velocity of the bar cross I2, which, well, we know the angular velocity, theta dot K cross I2. K cross I is equal to J, so we get L theta dot in the J2 direction. Okay, so now going and calculating these powers, right? P1 is F dot V, right? So it's minus F in the J direction dot the velocity, right? So that's L theta dot in the J2 direction. So when I go and work out these cross products, and maybe you could pause the mechanism or pause the video right now and figure out what J2 is in terms of I and J, right? It's relatively straightforward. We've done this 1,000 times. We end up finding that this becomes minus F L theta dot times cosine of the angle, right? J2 here minus sine theta I plus cosine theta J. P2, well, that one's actually pretty easy because both T, the torque, and the angular velocity are in the same direction, right? In particular in the K direction. So we have T in the K direction, dot theta dot in the K direction. K dot K is equal to 1, so that's just T times theta dot. Looking back at our power equation, right? P1 plus P2, well, that's minus F L theta dot cosine of theta plus T times theta dot has to vanish equals 0. So we can use this relationship. Now, one important aspect of this is that I don't know what theta dot is. So notice that in both of these kinematic parts, right, the velocity of P and the angular velocity of the bar, I have this unknown theta dot term. I never said how fast the bar is moving. I'm just trying to relate the force and the torque. So in a sense, I don't know what the velocity is, right? Because I don't know what theta dot is. However, if you look at this power equation, you'll see that theta dot doesn't matter. It appears in both terms, right? So I could factor that out and it cancels out of both terms. So it turns out that even though I'm using the velocities, I'm using the angular velocity, I'm using the velocity of P, I actually don't need to know what those values are. I just need to know how they relate back to a single coordinate. And then that coordinate, theta dot in this case, will cancel out of the power equation. So at the end of this, I can relate the force and the torque. In particular, I could go and solve for the torque. The torque here is equal to L cosine of theta times F. So you tell me the applied force, and I'll tell you the torque that's generated on this linkage. Really important point, though, is that that relationship depends on the configuration. So as the angle of this bar changes, then this relationship between force and torque changes as well. Also important, as I just mentioned, though, it doesn't depend on how fast the bar is moving, because that theta dot term canceled out. So using the power, using the kinematics, we're actually able to relate forces and moments without directly addressing static equilibrium conditions. I think that's kind of cool. So let's look at a more complicated example, right? That example is pretty simple. And in particular, let's look at an example with a single degree of freedom mechanism that has some complexity as given here. Turns out this is just a slider crank where link 3 is a little bit longer, right? But if you look at O2 to A to B, right, that's a fairly familiar slider crank kind of mechanism. So here, I want to apply a vertical force to the end C, and then I want to calculate the force that ends up applied to the slider. Right, so here F1 is going to be 200 newtons, and I want to find F2. Again, you could do this with momentum balance, right? So some of the forces equal zero, some of the moments equal zero. You'd have a bunch of reaction forces at every single pin. You'd have constraint forces here at the slider. You get a bunch of equations and then you could go and solve. Well, here we'll end up doing the same thing, except we don't have to worry about any of those reaction forces, right? Because they're taken care of by this power equation. Just kind of as an aside, the reason that the reaction forces don't appear is because reaction forces do no work. So they don't add to the power equation at all. But again, here in this problem, the external power vanishes, right? So P1 plus P2 has to be equal to 0, where we'll define P1 as the force. P1 here is a scalar quantity. It's the force, which is a vector quantity, F1, dot the velocity of the point that it's applied to, so that's c. And P2 here is the force F2 dot the velocity of the point that it's applied to, b. These are vector quantities. You cannot calculate the power properly unless you account for the magnitude and direction of both the force and the velocities. So we have to go through and look at these things in terms of vector quantities, right, as we've been doing throughout this entire class. So first, let's go and figure out what we need to calculate in order to apply this power equation. Well, I need to know the forces, which, I know F1. F2 is my unknown force, right? But I know the direction. I also need to calculate then the velocity of C and the velocity of B. So here, the velocity of B is the derivative of the position of B. Well, in order to do that, I need to identify the position vector. So here, the vector from O2 to B has known direction, right, but unknown magnitude. So we need a coordinate there, x. So again, the velocity is the derivative of position. And here, the position is x in the I direction. So that reduces to just x dot in the I direction, because of course I is a fixed direction. Now, the velocity of C is the derivative of the position of C. Well, C is up here at this bar, so in order to identify the position, I want to go from O2 to A. Well, that's going to require a direction vector, right? So let's go and define I2 as a long link 2. J2 is perpendicular. And then we'll define I3 and J3 along link 3. To that, we'll include a coordinate, say theta 3, that describes the orientation of link 3 with respect to I and J. So now, the position vector here is, well, it's a distance L2 in the I2 direction. And then minus, note that this sort of arm extending from A to C is a distance of D, and it's going to be in the minus I3 direction. So we get minus D I3. And then that equals L2 times the change in I2. Well, that's omega 2 cross I2. Here, looking at frame 2, we see that omega 2 is actually theta 2 dot in the K direction. This next piece is minus D times omega 3 cross I3. And let's highlight that, say, in pink. So now, when I go to determine omega 3, it's actually minus theta 3 dot in the k direction. If theta 3 dot is positive, then this frame of reference spins clockwise, and of course clockwise is in the minus k direction. So again, theta 3 dot positive, the angular velocity is minus theta 3 dot in the k direction. Okay, so using those two, we end up writing the velocity of c as L2 theta 2 dot in the j2 direction, right? Because k cross I is equal to j2, well, k cross I2. K cross I3 is equal to j3. We have two minus signs here, so we end up with plus d theta 3 dot in the j3 direction. So we've determined the velocity of B and the velocity of C. So now I can calculate actually these powers, right? So P1 here is minus F in the J direction, right? Because that was F1, dot the velocity of C. So L2 theta 2 dot in the J2 direction plus D theta 3 dot in the J3 direction. And so when I work this out, and again, maybe you want to pause the video and work out these dot products, but we end up with F1 times minus L2 theta 2 dot cosine of theta 2, right? That has to do with the J dot J2. And then minus D theta 3 dot cosine of theta 3. Likewise, P2 here is F2 in the I direction dot X dot in the I direction. All right, so this one's pretty easy. We end up with F2 times X dot. So at the end of this, P1 plus P2 becomes, let's do that in orange, well, it's minus F1 times L2 theta 2 dot cosine of theta 2, and then D theta 3 dot cosine of theta 3 plus F2 X dot equals 0. So this power equation ends up here boxed in yellow. And it can be used to relate F1 and F2, right? That's kind of what I wanted. I'm going to tell you F1, and I want you to tell me F2. In order to actually apply this, well, we need to know configuration. We need to know theta 2. We need to know theta 3. Theta 2 is given as 120 degrees, but I do have to do a configuration analysis to find theta 3. And then we also need to be able to relate theta 2 dot, theta 3 dot, and X dot with a velocity analysis. Okay, so we have to go through position and velocity analysis. Well, we always begin with the loop closure equation. Whether we are applying a position analysis or a velocity analysis or ultimately even an acceleration analysis, right? We start with the loop closure equation, which in this mechanism describes this sort of embedded slider crank, right? So it's R of A with respect to O2, right? This vector. Plus R of B with respect to A equals R of B with respect to O2, right? Which of course is this vector. We've already defined directions and coordinates and whatnot, So we can write this as L2 I2, right? That's A with respect to O2, plus L3 I3 equals xi. Then we want to determine the velocity equation. And this is the vector equation that describes the velocity variables. It comes from the derivative of the loop closure equation, right? So again, the loop closure equation is L2 I2 plus L3 I3 equals x in the I direction. And I just want to take the derivative. Or I want to evaluate how each one of these terms change. So we know how to take derivatives of vectors, right? And this one in particular becomes L2 omega 2 cross I2, right? That's the change in this first term. Change in the second term is L3 omega 3 cross I3 equals, in this case, x dot I. Well, look, I've already determined what those angular velocities are on previous slide. So now maybe if you want to, you can pause this, go work these cross products out, and what you'll find is that the velocity equations are L2 theta 2 dot in the J2 direction minus L3 theta 3 dot in the J3 direction equals x dot in the I direction. Right, so again, here we have the loop closure equation, which describes the configuration or the position, and then the derivative of that gives me the velocity equations. Looking back at this equation relating the powers, right, we do need to know theta 2 and theta 3. Theta 2 is given, but I need to go through a configuration analysis looking at the loop closure equation, right, or position analysis to determine theta 3. So here, again, loop closure equation L2 I2 plus L3 I3 equals x in the I direction. I just want to solve for theta 3. So I'm going to eliminate the other unknown, which here is x, by dotting this entire equation with j, right? Because j dot I is equal to 0. So we end up with L2 sine of theta 2, right? That's j dot I2, minus L3 sine of theta 3 equals 0, right? Or, right, we can just solve for sine of theta 3, right? And it's L2 sine of theta 2 divided by L3. You might recognize this as the law of sines. And for the values given in the problem statement, L2 is 20 centimeters, L3 is 40 centimeters, D is 20 centimeters. And at this angle, this becomes 0.433. So theta 3 is equal to 25.66 degrees. Right? So that's the angle in the clockwise direction of I3 from I. We can now actually go back and find x. We don't need it, but since we're here, let's just look at the component in the I direction, because we now know theta 2 and theta 3. Right? So in the I direction, I have L2 cosine of theta 2 plus L3 cosine of theta 3 equals x. Well, we have x directly from this equation. So for, again, this mechanism, x is equal to 26.06 centimeters. We've determined the configuration, but we still need to go through and relate theta 2 dot, theta 3 dot, and x dot, because that was part of the power equation. Okay. Again, here's the power equation, right? And we don't know what the input velocity is, but that's okay because any two of the velocity variables can be written or can be determined in terms of a third. Right? Or whichever one is left. Right? So I could solve for theta 2 dot, theta 3 dot in terms of x dot. I could solve for x dot theta 2 dot in terms of theta 3 dot, whatever I want to do. Here, let's actually go and solve for theta 2 dot in terms of x dot, and then theta 3 dot in terms of x dot. The reason is that x dot will then cancel out, and it will be fairly easy to solve for f2. Now, if you were to do something else, right, you would still get the right answer, right? Everything is fine. Just from an algebraic standpoint, this will end up being the easiest thing to do. But again, if you do something else, right, that's okay. You'll still get the right answer. So here, let's go back. I mean, this is our velocity equation. Right, so L2 theta 2 dot in the J2 direction minus L3 theta 3 dot in the J3 direction equals x dot in the I direction. Right, so let's solve for theta 2 dot, which means we want to eliminate theta 3 dot. Well, it's in a magnitude, right? So we'll dot with the perpendicular direction, which in this case is I3. Okay. We need to calculate I3 dot J2. L2 theta 2 dot. Well, when I do that I3 dot J2 dot product, right, I get minus sine of theta 2 cosine of theta 3. Again, you're following along, right? So pause the video solution or the video lecture and sort of work all this stuff out. I mean, in general, as you're listening to this, you really need to take an active role, right? So make sure that not only do you say, oh, I understand stuff, right, but that you can work out the steps that I'm working out as well. I dot I3 is cosine of theta 3 in this case. So now I can solve for theta 2 dot. Theta 2 dot here is equal to, well, in the numerator, I'll have cosine of theta 3. I'm going to wait and write the x dot at the end. And then the denominator actually is minus L2. Well, I factored out this minus sign. What's left really just becomes sine of theta 2 plus theta 3. You know, if you don't write it this way, that's fine. Ultimately, you'll be plugging in numbers, right? But I just think it's interesting to note that these angle addition formulas appear quite often when we're doing this kinematic analysis. Okay, so here's theta 2 dot in terms of x dot. Let's do the same thing to solve for theta 3 dot. All right, well, you know, we need the loop closure equation again, right? So just copy that over. And then we want to get rid of theta 2 dot. So that means that I need to dot with a perpendicular direction, which in this case is I2. Right? So that I2 dot J2 is equal to 0. Okay. Well, we end up with L3 theta 3 dot I2 dot J3 cosine of theta 2 sine of theta 3 plus sine of theta 2 cosine of theta 3. Again, that's taking dot products of different directions, equals x dot I2 cosine of theta 2. So once again, I can solve for theta 3 dot. And that becomes cosine of theta 2. And then in the numerator, like I did before, I'll notice that this is sine of theta 2 plus theta 3 times x dot. I mean, in this example, we have this sine of theta 2 plus theta 3 in the denominator of both pieces. That may or may not happen, right? It happens in this problem, right? So don't think that the numerator of one expression has to be, well, sorry, the denominator of one expression has to be the same as the denominator of the other, right? In this problem, these two things look very similar, right? But again, that happens because of this problem, right? It's not something that you can count on every single time. Okay, so we're almost done, right? Because I have my power equation. I have relationships for all of my kinematics, right? So again, here's the power equation. This is the relationship for theta 2 dot and x dot, theta 3 dot and x dot. I know my position analysis. So here I'm just going to start plugging stuff in. We'll simply take what we have and introduce it into the power equation. So minus f times L2 theta 2 dot. Well, theta 2 dot was cosine of theta 3 divided by minus L2 sine of theta 2 plus theta 3 times x dot, cosine of theta 2. And then d, we have cosine of theta 3 dot, which we solved as cosine of theta 2 minus L3 sine theta 2 plus theta 3 times x dot. And then cosine of theta 3 plus f2 times x dot equals 0. Okay, so again, as promised, the velocity variable that we're working in terms of cancels out, right? It's in every single term, right? So I'll just cancel that out. And as a result, we can solve for f2. We can actually do that directly here. And we find that f2, let's do this in pink, f2 then equals, well, minus cosine of theta 2 times cosine of theta 3. Notice that the L2's cancel out. Sine theta 2 plus theta 3 minus d over L3, right, from here, cosine of theta 3 times cosine of theta 2 divided by sine of theta 2 plus theta 3 times f1. Okay, so really at this point, all I need to do is take these position variables and put them into this expression. And when I do that, I find that this in parentheses is 1.211 and then times f1. I will remind you that if this configuration changes, right, so theta 2 was 120, if theta 2 became, say, 150 or 90 or anything else, then all of these angles will change. And as a result, the relationship between f1 and f2 will change as well, right? So f2 is not some constant fraction of f1. That constant of proportionality depends on the configuration of the mechanism. But finally, plugging in f1 is equal to 200 newtons. f2 is 242.17 newtons. So here we actually get an increase of the output force relative to the input force. And this constant of proportionality is referred to as the mechanical advantage. It's the ratio of the input and output quantities. If the mechanical advantage is greater than 1, as it is in this case, the output force is greater than the input force. If the mechanical advantage is less than 1, then the output force is less. If the force increases, that actually implies that the velocity decreases. While if the force decreases, you would actually get an increase in the speed, so that the power is the same from F1 and F2. Whatever power is put in by force 1 has to be taken out by force 2. So again, this is an example where we are using the kinematics, and in particular the velocity analysis, to help us relate forces for these ideal mechanisms. Well, that's it. Thanks a lot, and I will talk to you again.